Welcome to Chemistry at Hononegah High School. Today we'll be looking at our second set of notes from Chapter 6 dealing with the periodic table. And today we'll be looking at something that's really not covered as much as it should be in most textbooks. But if you understand these ideas, it really does set up the rest of the trends we're going to end up looking at in this chapter. And really what it comes down to dealing with periodicity and trends in the table is because the periodic table is arranged in a very ordered way based upon electron configuration, there's a number of very predictable patterns that exist in both chemical and physical behaviors on the test. In order to understand and use these trends, it's important that you really understand nuclear charge, shells, and shielding. And nuclear charge, another word for that, nuclear strength. So we've got three S's here, strength, shells, and shielding, that I really want you to have a concrete understanding of before we go forward. And what you need to understand is all trends are going to be explained by nuclear charge and shells and shielding. When you put these together, really all the rest of the stuff we talk about is going to come as a natural consequence of understanding them. So understanding individually as well as collectively what's going on with these concepts is going to really allow us to understand to a much greater depth exactly what's happening in the rest of the chapter. So first, nuclear charge or strength. Well, you need to understand what we're really talking about here is what's happening in the nucleus. Nuclear strength is dealing with the nucleus. And as you move across a period or when you go down a group, our atomic number is increasing. And remember, the atomic number is the number of protons in the nucleus. So as we're going across and down, our nucleus is getting more and more and more protons in it. Now that has a consequence because positive things attract negative things, and the more positive it is, the more strongly they attract those negative things through a process related to Coulomb's law, which is something in first year chemistry we don't really get into to any great depth. But really what we're looking at is the more protons, the more positive pulling power. And that's what we're looking at with nuclear charge that the nucleus has, and it's going to be increasing. So more protons, stronger positive pulling power. So if you put it together, think of all P's here. Nuclear strength is related to the positive pulling power of the protons. And that's going to have a huge impact on a number of our trends that we look at. So that's what nuclear charge or nuclear strength is. So our fundamental pattern, across it increases and down it increases. So that would be our trends in nuclear strength. And that's because we have more protons as we go across and more protons as we go down. Now, the second concept we're going to look at here that's core to understanding our other trends is shells. Now, shells is an old name for energy levels. And if you remember back in biology or in middle school when they would make the drawing of the atom with these rings around it representing the energy levels and they'd put in electrons, that's why we refer to them at one point as shells. So shells, just energy levels, another name for it. And remember from last chapter, the higher the energy level, the higher our N value, the farther we were from the nucleus. So your average distance from the nucleus increases as our number of energy levels increases. Now, what's happening with energy levels when we go across and what happens when you go down? Well, across we're adding to our valence level in the S&P block, or we're adding to an inner level D or F. So we're not doing anything to increase our number of energy levels when we go across a period. So across, it's constant and it's completely irrelevant because the highest energy level doesn't change ever when we go across a period on the periodic table. Now, when you go down, however, it's a different story. As we go down from period 1 to period 2 to 3 to 4, we add a new valence level. So we're steadily increasing our highest energy level, and we're therefore moving those valence electrons farther and farther and farther away from the nucleus as we add energy levels. And distance and how it affects attractions is a really important idea that we're going to end up looking at related to this. So those are our trends with shells. But all that's left is shielding. Now, shielding is the one that is the most complex idea. If you look at it in the right light, it's really not that bad, but you do need to understand exactly what I want you to be able to say on the test related to shielding. So we have our nucleus in the middle. That's where our protons are at. Now around that we have our energy levels. And this is just what I was discussing a second ago. So we've got our nucleus, and then around that we have energy levels. Now, on those energy levels, we have electrons. So let's look at a fairly simple atom like sodium. Sodium has one electron in its valence level, which is a third. So I'm going to put one dot there. Well, it had 2 electrons on the first level, and it had 8 electrons on its second level. So those are all the electrons and what energy level they're on in our sodium atom. Now, shielding is how these inner level electrons, all of the ones in this ring and in this ring. How those inner level electrons interfere with the nucleus's ability to attract and hold on to valence electrons. Shielding is dealing with that situation. So inner level electrons partially shield the valence electrons from the attraction of the nucleus. So there's three ideas here. So if I ask you to do this on the test, and hint, there's a 100% chance I'm going to ask you what shielding is all about, you need to have three components. It's about the inner level electrons, preventing the valence electrons from being attracted to the nucleus. Those are the three core ideas to this. And why do they do it? Well, think about it. Electrons are inherently all negatively charged. Well, negative charges repel each other. So all of these electrons in the inner core level are all repelling those valence electrons and each other away from that nucleus. Now, a valence electron can also add and repel. But when it's on the outside, it really isn't repelling effectively compared to the core electrons. So really, when we're looking at shielding, we're looking at those core or inner level electrons because they're packed in between the valence electrons in the nucleus, and their electron repulsions are significantly affecting the nucleus's hold on those electrons. So that's what shielding really is. It's the inner level electrons repelling and preventing the valence electrons from being attracted by the nucleus. Now, when you go across, think about going across your S&P black. You're adding valence electrons. And remember, I just said a second ago, electrons on the outside aren't as effective at their repelling ability. So when you go across, shielding is relatively constant. And that's because we're adding, let me say this correctly, we're only adding valence electrons. So let's get rid of that not right there right now. So going across, we're adding valence electrons, and those don't really increase our shielding or our screening all that much. Now when we go down, however, as we go down from one period to another period, to another period, to another period, we keep adding a valence level and increasing our number of inner levels, which are now filled with electrons. So when we go down, there is a definite effect with shielding. So shielding is going to steadily increase as we add more and more and more inner level electrons when we're going down a period. So across, it's relatively stable. Going down, however, it increases significantly. So when we put these two together, they both did the same thing across. They were constant. And they both did the same thing down. They were increasing. Now, those are our three core ideas: nuclear strength, shells, and shielding. But these are all happening together inside an atom. So what we really have to do is look at how one affects the other, because we're actually talking about competing forces here. Shells and shielding are doing things that can diminish the attraction of the nucleus. So we have basically two competing forces here. And what we're looking at is overall what's happening. So we need to look at nuclear charge versus shells and shielding. And when we put them all together, what happens? Well, first we're going to look at the period trend. Remember, across the period, the nucleus got stronger. Shells and shielding were constant and did nothing. Well, that means they can't affect the situation. So the only thing that's important when you go across is the nucleus is getting stronger. So in a period trend, we're going across a period of the periodic table. Nuclear strength is the only thing that is important and relevant. So our nucleus is getting stronger and stronger and stronger as we go across. And that's going to have a variety of effects on different trends in the periodic table. So remember, because shells and shielding are constant across a period, they don't really affect the period trend. And what we're left with is the nucleus is getting stronger. Now, what happens in a group situation? Very, very different. But before we move off the period, I want to remind you of one important thing. Capitals, and it says all. That means there's no exceptions. Every single time we talk about something happening across a period, the reason why is always going to be about effective nuclear strength. So if you inherently are comfortable with the fact that the nucleus gets stronger when you go across, it's easy to see how all of our trends get created. As long as you remember that increasing nuclear strength is the critical thing when we're going across a period. Now, with a group trend, like I said, it's a different situation because now nuclear strength is increasing and shells and shielding are increasing as well. But what you need to understand is effectively the shells and shielding are going to win here. Now, why? Well, you need to understand a very specific series of reasoning here. Now, even though our nuclear charge is increasing, there's also an increasing in the shielding. And remember that shielding is the inner level electron repulsions interfering with the nucleus' ability to hold on to things. So what really happens is those two things cancel each other out. So when we're going down, Shielding and increased nuclear strength basically are a cancel out situation. And all we're really left with is the fact that we've got more shells. And what you need to understand is the consequence of that situation. So one, more shells means you're farther away from the nucleus. So if we're talking about atom size or ion size, as you go down, they're going to get larger because your valence level is farther from the nucleus. That means it's bigger. The other thing you need to understand is distance kills attractive forces. And what we're really looking at is how the nucleus is holding on to things. So when we go down and we increase our distance from the nucleus that our electrons are existing at, they're going to be holding onto those electrons significantly more weakly because of our increase in distance. That's actually another application of Coulomb's law, is the idea that distance kills attractive forces between oppositely charged particles. So remember that idea. Distance kills attractive forces. So when we add more shells, we're going to end up diminishing how strongly the nucleus can hold on to the electrons that are farther away from it. Now, just like with the period trend, same thing is going to happen here with the group trend. All of our group trends then are going to be caused by the fact that nuclear, or I should say by the fact that we're increasing our number of energy levels. So all of our group trends are going to be caused by increasing shells and its effect on really what it does to the nucleus's ability to hold on to things when they're farther away. So what's happening when we put all these together? Well, when we go across, nuclear strength increases, and that's all that's important. So the nucleus is getting stronger. But when we go down, and remember, you need to think of it in the right order here. While the nucleus is getting stronger, it's canceled out by the increase in shielding, and those two things are a wash. And what ends up happening and becoming important is our shells are increasing when we go down. And that's really the key idea we're going to use in every across and every down situation. So as we get into atom and ion size and so forth in our next set of notes, that is really an understanding of these ideas are going to be critical to understanding atom size, ionization energy, and electronegativity.